Hello everyone. Today I wanted to continue with our discussion about TrueBit. So in the last class we said that we have a task giver. So this task giver puts a CIT, a computationally intensive transaction on the blockchain. Right? So it gets in somewhere into the blockchain, but we said we do not want the miners to do this computation. The miners will compute all the other transactions which are not CITs, but this CIT will be offloaded to somebody else who can do the computation, and that person would have to return the result. And okay, so this might go on to the blockchain as a transaction. There may be other transactions. So we want some volunteer who we'll call a solver to do the computation and return the result. So the blockchain is going to be used here as sort of a whiteboard on which people can cooperate and sort of communicate with each other. Right? So the solver can post a transaction which goes into a subsequent block, right? And the result is over here. Okay, so let's say that the result is given in the form of a hash, okay, which may be the hash of the state of the smart contract for which this CIT belongs to. Okay. And this is how we want the whole system to work, so that the miners themselves are freed of doing heavy computation. The validation time for this block is going to be small for them, so they don't have the verifier's dilemma. The tricky part is, how do we know that the solver has done this correctly? In a system like Bitcoin or in the current Ethereum, all miners evaluate all transactions in the block, and they themselves verify that the state is correct. Okay, so they have an incentive to do that, because if they include, let's say, an invalid block in their blockchain, then they will be mining on an invalid chain, and that is not a clever thing to do, because other miners will reject any block created on a parent which is an invalid block. Right? So all miners in Ethereum and Bitcoin are incentivized to evaluate all the transactions. Okay, and the time to evaluate is quite small, so it's worth doing it. You don't want to be mining on a block which is invalid. But in this case, the miners have not done the computation of this CIT, so they don't know if the result is correct or not. The solver might put some rubbish on the blockchain, and that's going to defeat the whole purpose. You want the correct computation to be done over here. Okay. So how do we know that the solver has done the computation correctly? And one way to do it is that you have some verifiers, we can call them challengers. So challengers are other parties. I can just say some parties who will challenge the solver's result if it is wrong. Okay, so what we are saying is that there will be some other people, let's say some group of people, we don't know who they are, okay, but let's say that they also do the computation for some reason, and if this person has submitted a wrong result, then they challenge. So they challenge the result. That could happen in some subsequent block, right? And then the solver can be punished if at all, let's say the challengers were correct. Okay, so this is sort of like an incentive to get the solver to behave himself so that he submits the correct result. Okay. Okay, and here let's say that the miners, so there are other blocks over here, miners decide who was wrong and they punish whoever was wrong. The guilty party. Okay, so we haven't yet gone into the details of how exactly all of this works, but this is at a high level what is to be done. So there are several problems which come up. So first of all, why would anybody else be doing the computation? So just think about, so we said the solver is chosen, we said in the last class, a lot of people can volunteer to be solvers. So they just transmit transactions onto the peer-to-peer network, we said last time. And the first person whose transaction gets into a block becomes the solver. That is what we said. Okay? And so now everybody knows who the solver is. Okay, you know whether you are a solver or not. You know, you may have volunteered to solve it, but your transaction didn't get into the blockchain, and you didn't become the solver. Somebody else beat you to the game, right? And he became the solver. So the solver is chosen by whoever mines a block and includes the first transaction among those who volunteered to be solvers. So why should anybody else do the computation? You know, if I am not the solver, why should I bother doing the computation? So the thing is, normally if everybody is rational, only one person would be the solver and would do the computation, and nobody else would check whether the solver is doing it correctly. So there wouldn't be any potential challenges, right? So this is the dilemma we are in. Why would anybody challenge? And if there is no reason for somebody to challenge, then there's a very big danger. The solver could be malicious or, you know, just lazy, and he just doesn't do the computation. He just puts some junk result over here. So this is a very big problem, and we didn't have this sort of a problem in Bitcoin or Ethereum, right? The typical Ethereum, because all the miners are verifying everything, right? So how do we get challengers in the first place? And this is where the innovation of TrueBit comes in, is that it says that I will ensure that once in a while this solver is forced to submit a wrong result. Okay, and which means that this whole process would go through, right? And this solver would, let's say, get punished, let's say, right? But his money would be taken away, right? And this, of course, this money would go to the challengers. Okay. So it's a very counterintuitive idea. So let me just write down the issue. So how to ensure that there are, let's say, some others who do the computation besides the solver. So what TrueBit does is it ensures that if that whole procedure goes through, you have solver submitting result, challengers challenge, it ensures that the challengers will get some payout over time. So TrueBit ensures that the challengers get a payout over time. Okay. So this is the idea is that once in a while the challengers are going to get some money. So how we do that is, we'll see, it's a little bit tricky, but it's like telling people to mine blocks, right? So people keep trying to mine blocks and most of the time they don't mine the block, right? But they know that once in a while they're going to have a chance to get some money, right? Which is why people mine for Bitcoin and Ethereum and so on. And that's the same idea over here, that once in a while you will get some money. That is what your TrueBit is going to ensure. So you are incentivized, anybody who might be incentivized to become a challenger because there is some money to be obtained. Okay, so solver is going to submit the right result most of the time, right, and you don't get any money. But that's true even for mining blocks, because you mine most of the time but you don't win the game, right, but still you do the computation and so on. But once in a while you mine a block, and here too, once if you're a challenger, if you want to be a challenger, once in a while you will get some payout. Okay. So how do we do that in this scheme of things? So we said that the solver submits a result and then somebody could challenge. Of course, it's possible that nobody challenges also. But if the result is wrong and you have an honest person who's a challenger, he will challenge. And then there will be a payout, right? And the miners, so we assume that the miners are trustworthy. Right, and the miners are going to decide somehow who was right and who was wrong, right? And they're going to make the payout. Okay. So it's a very complicated procedure, right? Normally, within this block itself, the transactions are evaluated and the state is updated in Ethereum. But here for the CIT, it takes very long to get the result, right? And the result could be challenged and so on. So this is sort of a trade-off, that you can do heavy computation, but it would take a long time for the rest of the network to know what is the final result of the CIT. So how does TrueBit actually ensure that all of this happens? So what TrueBit does is very tricky and very interesting, in fact. So what they say is that the solver submits two solutions. Let's say a solution which is true and a solution that is false. So previously we just said that the solver submits one solution, but TrueBit does it in a little bit of a different fashion. So the solver is forced to submit two solutions, one which is true and one which is false. Okay. And you want the solver to do the computation correctly. So if he's an honest solver, it's in his incentive to submit a true solution. Definitely he would want one solution to be true, and of course TrueBit says you have to submit something that is also false. And so suppose he has done this, he has submitted two solutions and not one. What the TrueBit system does is that it randomly chooses one of these as the solution of submitted by the solver, sort of the official solution. Okay, so let's just put it this way, that one of these is sort of like randomly chosen, either one of these. Okay, so how this is going to happen we'll see in a moment, but effectively what's going to happen is some random bits are generated in the system, and the solver is later, based on those bits, he's going to have to essentially choose one of these. So he'll have to tell everybody that okay, originally I submitted these two solutions, but now I'm saying that this one is my solution. It could be SF or ST. Okay, so a bit is going to be chosen, which is going to essentially force the solver to point to one of this. Okay, and that's where the term true bit comes into the picture, right? So some random bit is created out of the system, and one of these two, the solver is going to say is my solution. Okay. So suppose he has chosen, let's say this one, right? So the bit has forced him to say that this is his solution, and you would want this to happen, let's say, most of the time. Okay? So then what happens? So there are some challengers. Some people have also done the computation hoping that they may get a chance to challenge, but then they say that he has done it correctly, so they will not challenge. Okay, and so assuming everybody is honest in the system, ST implies there is no challenge. There's something wrong with my pen over here. Okay, so assuming the challengers are also honest, none of them are going to challenge, and everything goes through, right? But it may happen that let's say that this one is the one which the solver will point to, right? And in which case the challengers are allowed to challenge, okay, so there are some challenges, and then of course the miners will have to jump into the whole scenario, and they'll have to decide who was correct or not, the challengers or the solver. Okay, and that is going to they're going to go through some procedure, and then they will potentially reward the challengers, assuming that these people did the computation correctly. Okay. So it seems a very elaborate system, and let's look at the details how to do this, right? But what you want to do is the system ensures that once in a while the solver is forced to point to the false solution which he has submitted, in order to guarantee some payout to the challenger, so that they are incentivized to challenge. Right? And it's something like POW, that that you're going to win once in a while, so you might as well try to do the computation. Okay? So many issues come up, and we'll see them after we discuss what exactly TrueBit does. Okay, so let's actually draw the system. So let's say that the task giver has submitted the CIT. Somewhere in the blockchain. And there are lots of volunteers who generate transactions saying that I am willing to do the computation. And one of these, let's say, is chosen and it gets into the blockchain. Right? And the person who created this is going to become the solver. So he is the creator of the transaction, of the I should say the volunteer transaction. So we are using the blockchain as sort of a whiteboard for communication between different people, right? So the task giver has put his CIT as a transaction here, and here the volunteers they broadcast the transactions to the peer-to-peer network, but only one of them gets into the blockchain according to the rules of the system, right? Nobody is allowed to submit any one of these transactions, okay? Any other one once one particular transaction gets. Okay? So now the solver is chosen, and now comes the tricky part. How do we do this whole thing of true bit, right? So we have to be able to choose a bit somehow which is going to decide which of ST and SF are going to be considered the official solution of the solver. Okay? And it's a tricky thing that we do not want the solver to know in advance what the bit is going to be. So what is the bit going to be? Is it pointing to, so is it going to say true or is it going to be false? So the bit is true, of course, it means that ST is the official solution, and if it is false, then SF is the solution. So we do not want the solver to know this before he submits ST and SF. And why? So why would we not want the solver to know the bit before submitting ST and SF? Well, think about it. If the solver knew that the bit is false, then that means that this SF would be his official solution. So why bother doing the computation correctly and submit ST? Okay? So we want the system to work such that the solver, if he's a rational person and doesn't want to lose money and so on, he will always submit one solution ST which is correct, and SF is going to be the other solution, right? Some false solution. If he knew that the beforehand itself that the bit is going to be false, then he would submit both false. I mean, it doesn't matter what this is going to be in that case, because if this one is chosen, then the challenges and other things are going to depend on this. It wouldn't matter what he has submitted here. Okay? So we want the solver to not know what the bit is going to be initially, right? And okay, so we'll have to figure out how to get this to work. Also, we do not want the challengers, potential challengers, to know the bit before they submit their solution. Okay, so we want the challengers to be able to do the computation honestly, right? So it's as if they don't know what the bit is going to be, and they will have to uh, submit, let's say, their solution if they think that this SF, if at all the bit is such that this one is being pointed to, that they will actually submit their solution. Okay, so we do not want the challengers to know the bit. Before submitting their challenges. Okay. So of course, if they think that the solution submitted by the solver is true, then they don't have to submit any challenges, right? But anyway, we want them to be in the dark. We want them to sort of just see that there was this solution that was submitted. Even though they were not chosen as a solver, they do the computation themselves, right? And then they just wait and they see, has the solver finally will point to what is his solution, and they see that okay, he has pointed to SF, and that is the false solution, and so we are going to challenge it, right? And in the hope that they're going to get some money, right? Okay, so this is tricky. So we are saying that let's say that the let's say that here solver is going to point to ST or SF. Okay, based on what the true bit is and so on. Okay, and then we have challenges. Okay, so what we are saying is that at this point in time, solver must know the bit, because based on what the bit is, this bit, whether it's true or false, he will have to point to ST or SF, right? But the challengers should not know what the bit is, because they are going to submit their challenges later over here, right? And so they, they see that SF has been pointed to and this is not the solution which matches what they have calculated, they can submit their challenges, right? But at some point the bit needs to be revealed to all, right? And here the miners are going to distribute some money. Okay, so what is going to be done is, if the bit is false, what is going to happen is that only money is going to be distributed among all who have challenged. And so there is something called a jackpot. I haven't mentioned it till now. So this jackpot is like it increases, let's say, over time. So what we're going to do here is that the solver points to ST or SF because he knows the bit, but the challengers don't know the bit, so they submit their solution. The bit is revealed to all over here, and then if the bit is false, then the jackpot is distributed among the challengers. Right? And now if the bit is true, then we are in a quandary, because that means the solver should have been pointing to the correct solution, but at the same time there have been some challengers which have challenged. And of course we are assuming that there are some challengers, right? So if the bit is true, then the miners have to decide between challengers and the solver about who was correct. So of course, if the bit is true and there are no challenges, then miners don't have to do any extra work, right? It's just that whatever fee had to be paid for the solver for doing the computation, he will get it. Okay. Okay, so how do we do this? Because it seems that not everybody gets to know the bit at the same time. The solver gets to know the bit before the others, and then the bit is revealed, right? And we said that when the solver submits ST or SF, that would be somewhere over here. Okay, so at this point in time, ST didn't know the bit. Okay, so how are we going to do all of this? So initially ST doesn't know the bit, but initially the solver doesn't know the bit, then the solver gets to know the bit, later on everybody gets to know the bit. Okay. So how is this going to be done? Well, what TrueBit does is that, let me use the same figure. Okay. So we want the bit to be a function of some information which only the solver knows initially. Okay. So that at this point in time, people don't know that hidden information, but of course the solver knows it, right? And he knows the final bit, whereas here that solver is forced to reveal that information so that everybody knows what the bit is. Okay, so what is done is that here some information is submitted by the solver, so the solver submits hash of some R, where R is only known to the solver, right? So even though people have seen hash of R, they don't know what R is, right? Only the solver knows it. Now what is the bit? So after the solver has submitted solution, let's say that this is there in some block. From the next block, so there is some hash of this block. Right? So this hash value, okay, and is concatenated with R, okay, and we take a hash of this, so I just say this is the block hash of this block concatenated with R, and the hash of this is used to generate the bit. Okay, so maybe it is just the most significant bit or the least significant bit of this hash bit, right? And of course later on here the solver is going to say that which of these two, he's going to submit a transaction which is going to say which of these two solutions of his should be considered as his official solution, okay, depending on what this bit is. If the bit is true, he's supposed to point to ST. If it is false, he's supposed to point to SF. Right? So we see that clearly that at this point the solver knows what the bit is, because he knows the value of R and he knows this block hash, right? So he can generate the bit. But other people do not know what R is. They only know what the hash of R is. Right? So the challengers don't know what the bit is. So, and they just see that if their own solution doesn't match what has been submitted here, for example, SF is the official solution, so they might challenge, right? And now, of course, at this point in time, we want everybody to know what the bit is. So how is this done? Well, the solver reveals R over here. So the solver has to publish another transaction which contains R, and people will see that indeed it matches with what he submitted here, right? And of course, if he publishes something wrong, or if he doesn't publish, then he would have to be punished, right? And okay, and here of course the miners might have to step in the case where the bit is true, and still there have been at least one or more challenges on the solution submitted. Okay. So very elaborate scheme of things, and when you have such a complicated system, then obviously it opens up more and more attack surfaces. Now let's look at this situation. So suppose the bit was true, and so this was ST was what the solver pointed to, but there were non-zero number of challenges. And at least one challenge. Now the question is, the miners have to decide whom to punish, right? Because let's say, to simplify it, let's say that there is only a single challenger, right? If there are multiple challengers and the challengers themselves give different solutions, then it's a big headache, right? But so assume that there is one challenger for now, okay? And what we want to do is we want to punish the solver if he is wrong, right? And we would like to punish at least one of them, right? So we are never going to be able to find out who is correct over here, because the miners themselves are not doing the computation themselves. Okay. So we want to punish one of the wrong parties, let's say. That's what we are hoping to do. Okay, and so suppose the challenger we are considering is correct, then we would want to punish the solver. But suppose the solver was correct and the challenger was wrong, then the challenger is going to be punished, right? And if, of course, if both of them are wrong, then at least one of them we want to punish. Okay, at least, I should say. So how are we going to do this? And so what I'm going to draw here is something called an execution trace. So what is shown on this line over here is, this is the first instruction. Okay. So these are the steps of the execution, and I'm going to start with the 0th, let's say the first instruction is executed here of the CIT. Right, and I go on in this way. Okay. And let's say that the execution ends at step T. Okay, and it may be, of course, that the solver stops at a particular T and the challenger says that I stopped at another T. Right? Okay. So you see that. So these are not exactly let's say this is not the instruction number of the CIT. I mean, so you're continuously executing the CIT, and what is shown here is the particular execution step. So let's say that I'm at execution step some E over here, right? And corresponding to this, let's say the solver has a particular instruction which he's going to execute next, right? And of course the challenger also at this particular instruction E, he is going to execute some instruction and then go on to the next one and so on. Okay. Okay. So this is the execution, and let's say this is the teeth. At the teeth instruction step, let's say that the solver stopped. Okay, and maybe to make it simple, let's say that both stopped at the teeth at the instruction step, right? Or the teeth execution step, I should say. Okay. So now both of them have this execution trace, and we do not want the miners to do all the execution. So what they are trying to do is they are going to try to find out where the challenger and the solver actually disagree. So okay, there is no disagreement over here because both start at the first instruction of the CIT, right? There is no question about that. But if they end up with different solutions, then somewhere in this execution trace they would have had to differ from each other. Right? So the goal is to find this position where they first disagree. So the first step of disagreement. And how to do this? Well, now there's going to be a game played, right? So if this particular condition is true, at least one challenge, and let's say that the bit came out to be true, what the miners will ask is they will ask both the challenger and the solver to tell them what their state was, and they do a binary search, right? So they might say, tell me what was your state over here at T/2. And they will see if both of them are the same. Of course they would do the search over here, right? But in this case, let's say this E is to the left side, so they see that both of them differ, so they go to this position T/4 and they ask them, and they see that both of them submit the state, okay, their state at this particular point in the execution. And so they do a binary search and they zero in on this particular point in the execution trace where they actually differ from each other. Okay. So now they will say both of them have to submit the state at E-1 and E. Okay, so by definition, both of them must have had the same state at E-1, right? Because E is the first step where they are actually disagreeing. Okay, so this step also has the instruction, I mean the state also has the instruction in the code which is going to be executed next to go to this, right? So now here the miners know what is the agreed upon state over here. So they execute the instruction, right? So the instruction is also part of the state, right? So both of them agree on what is the next instruction to be executed. And the miners are all going to take this state and they are going to execute that instruction, and they see what is the new state. Okay, and then they are able to see who gave the actual correct state corresponding to this. Okay, so they are going to use this to decide which of them was wrong, right? So it's, let's say that the solver has submitted the correct solution, so they will see that the challenger is wrong, okay, because they're able to find how to go from E minus 1 to E. Okay, so it's a very, very tricky situation. So they both the solver and the challenger have this execution trace with them. Okay, but the miners don't want to be bothered with the entire execution trace. So they do a binary search. They tell both of them to submit their states, and they find out the first location in the execution state where they disagree. Okay, so they take the E minus 1 is where they've agreed. So they take that state from both of them, and they actually execute the instruction corresponding to that particular E minus 1. Okay, because we said that the particular instruction to be executed next in the code is also part of the state, right? And they're going to decide who was correct over here, right, and who was wrong. And we are assuming that only one of them was, telling, one of them was telling a falsehood. So that particular person will be punished after this. Okay? So all this back and forth communication between everybody has to happen on the blockchain in the form of transactions. So this can take a lot of time, and as you know, binary search takes log T steps, right? So you would expect order of log T communication to take place. For the binary search. Okay, and this is going to help the miners decide who was wrong. So the miners themselves will only have to execute one instruction of this CIT, that is to go from E minus 1 to E. Okay, but this doesn't guarantee that the person who, let's say, who had the correct state at E has indeed submitted the correct solution, okay, for the full CIT. Okay, it's possible that, for example, that the solver submitted has the correct state at E, but it did something wrong after this, right? And so the ST which corresponds to this might actually be wrong. Okay, so we are not sure in this whole procedure who was correct, but we're at least able to punish one of them who was wrong. Okay, and it might also happen that when we execute the instruction to go from E minus 1 step to step E, we find that both actually have the wrong state over here. That might also happen, right? Okay, so anyway, TrueBit is going to ensure that at least one of the persons who has submitted a wrong solution is going to be punished. Okay, and it has to do this with this order of log T search, binary search, to find out who was wrong. Okay, so it's a very complicated situation, right? A very complicated protocol, and so many different things can happen over here. There may be lots of attack surfaces opened up. We'd have to think, what if the solver wants to also be a challenger, right? What mischief could you do? right? Or what if there are like a million people who have submitted challenges, right? What is going to happen in that case, right? So we'll discuss a little bit about that in the next class, and we'll start also talking about Yoda, and we'll see how Yoda resolves some of the issues that TrueBit has.